We are going to work on a new method of volume, and it's called volume by the method of cylindrical shells. And over here we have a picture of a bundt cake. I'm sure some of you guys have seen one of these at some point. So our first example is actually going to be based on this, and we are going to find the region that is bounded by the x-axis, y equals to 3x minus x squared, and we're going to take that and revolve it about the line x equals -1. So first let's take a look. X equals -1, which is what we're revolving around. It's going to be a vertical line, not on our y-axis. And the curve y equals to 3x minus x squared, this is going to be a parabola that opens down with x-intercepts of what? 0 and 3. So at 0 and 3, we are going to have a parabola that opens down. And this is not going to be drawn perfectly to scale, but we're going to take this piece and revolve it around and spin that around. And I hope you can see that it's going to create our bundt cake, just like above. And this region, when you spin it around, like if you were to take a point up here, it's going to revolve and go this way. This point over here, when you revolve it, it's going to come around. Now, the problem we have here is that we cannot use the method of washers on this one, and I'd like for you to take a look and see why. Because if we did the method of washers, which would be this diagram right here, what would our big R be, and what would our little r be? Well, big R is based on the parabola, which is 3x minus x squared, but little r is also based on the parabola, which is also 3x minus x squared, which is a problem because big R minus little r, or big R squared minus little r squared, would equal 0. And that would be a bad thing, because obviously the volume is not equal to 0. So I'm going to go ahead and draw this again. But this time, we're going to use a different method, and this one is called shells. So the way that this works is that you are going to take any point on your curve, x, y, and much like finding area, like if I asked you to find the area under this curve, you would most likely be using dx and finding this piece as opposed to horizontal sections. Okay, so what is the length of this piece that I've drawn in my shaded region? Okay, well this would be y. And from this point, I want you to go ahead and draw the segment to your axis of revolution. So in this case, this little dotted segment over here, and this is actually going to be how long. How long is this piece right here? Look carefully. This value is our x, but I have an extra piece here, so that's going to be 1 plus x. Now I'm going to take this piece and I'm going to spin it around the axis. So this piece is going to revolve and come over here. And I am going to be creating a cylinder. Okay, so we have the shell radius, which is x plus 1. We have the shell height, which is the y value, but we're going to write this out in terms of the function, so 3x minus x squared. And we can take a look at the shell as being, imagine it as a soup can label that we're going to unwrap and lay flat, so that this is its height, and the shell radius, which is x plus 1, will be part of our circumference, which is 2 pi r, or we'll write it out as 2 pi times x plus 1. And here I'm going to write the height out as 3x minus x squared. So this would give you, when you multiply those two together, the area of each one of those pieces, which is going to be 2 pi x plus 1 times 3x minus x squared. And you'll hear me often refer to that as 2 pi shell radius times shell height. So keeping in mind that volume is always going to be the sum of all of the areas, and in this case they're shells. That'll be 2 pi RH dx in this case. So we'll have 2 pi times x plus 1 times 3x minus x squared dx, and this should be a fairly easy integral for you to work out. And we need to also think about our bounds. Now, where's the smallest radius going to be? It's going to be over here on the left-hand side of our parabola where x equals to 0, and it's going to get larger up until you hit x equals to 3. So if you want to work this out and integrate it, the answer is supposed to be 45 pi over 2 units cubed. All right, let's try one more example. I want us to find the volume of the solid generated by revolving about the y-axis, the region bounded by y equals to 3x minus x cubed, the y-axis, and the line y equals to 2. Now I'm going to go ahead and give you this diagram because it's a little bit tougher to draw. Y equals to 3x minus x cubed. But it looks something like this. It's a cubic function. And we're going to say that this point right here is 1, 2. And I want to revolve the region bounded by the curve, the y-axis, and the line y equals to 2. Now this little region that I want to revolve is going to go around the y-axis this time. So I'm going to kind of draw a representative piece over here on the left-hand side. And if you notice, it looks like we could use discs. Wouldn't it be nice to have discs that are stacked? If we were going to use discs, our volume would have to be the integral from a to b of a of y dy. And that would require me to write this equation as an x equals 2. Notice it's a little bit tricky for us to do. I can't really write this out as x equals 2 because I've got x in 2 places. So just like last time, we are not going to be able to do this with a method that seems like it would be pretty easy from before. We already know that, this method, but it's not going to work. So let's go back and rethink this. We can actually use our method of cylindrical shells here. What I need you to do is draw a point on the curve, xy, and let's figure out how we can represent the shell height and the shell radius in our shaded region. So let me draw this little piece, just like finding area, so I'm going to draw this little rectangle. Now the x-coordinate is how far over we go to the right. Our y-coordinate is how far up we are from the x-axis. So notice my shell radius is actually our x-coordinate. That's kind of nice. But our shell height is not y. Notice how y is outside of our shaded region. Our shell height is actually 2 minus y. So we're going to write this out as 2 minus 3x minus x cubed because we're going to need it in terms of x. So 2 minus 3x plus x cubed. And our shells, if you want to see what the shell looks like, it's going to look like this cylinder. So the volume is going to be the integral of 2 pi x, which is our shell radius, times our shell height, which is 2 minus 3x plus x cubed dx. Now where is our smallest shell? It's when it's sitting right here close to the y-axis. So that means we have x value equal to 0. And the largest one is going to be out here on the outside tip on the right-hand side with an x value of 1. So again, you can take this and you can integrate it on your own. It's going to equal 2 pi over 5. We're going to take a look at one last example, and that's going to be the region bounded by y equals to x squared, y equals to 1, x equals to 2, and we are going to revolve it about y equals -1. So this one's going to seem like a pretty simple, straightforward region, y equals to x squared. But it's going to be also bounded by y equals to 1, which is a horizontal line here, x equals to 2, so like this. So can you guys see the little region? It's right in here. So when we revolve it about the horizontal line, y equals -1, be really careful. The region that gets revolved is going to move and be down here. Okay, we're going to revolve it all the way around. Notice this time we are revolving around a horizontal line. The other two problems that we did, we revolved around vertical lines. If we were trying to find the area of this one, I would not be looking for vertical sections, I would be looking for horizontal sections. So I'm going to draw my horizontal piece over this way, sideways, and a representative point on my curve, which is xy over here. X is the amount of space over from the y-axis, and the y is the number of spaces over from your x-axis. Our shell radius goes all the way to the axis, and our shell height is actually sideways this time, because our cylinders are actually lying down. They go all the way this way. Kind of hard to see. You might want to tilt your head to the side to look at this. So our shell height is not our x-coordinate, but instead this vertical line is x equals to 2. So our shell height is going to be 2 minus x. Our shell radius, which goes all the way down to the axis of rotation, is going to be our y value plus a little bit extra. How much is this piece? This is our x-axis. This is the horizontal line, y equals to -1. So it's going to be y plus 1. Okay, our volume is always going to be the integral of the sum of our areas, but this time our areas are going to be written out with respect to y because our shell is sort of lying on its side, where this is our shell height, and our length of this here is 2 pi r. Our circumference is going lengthwise. So the area will be 2 pi shell radius, which is going to be y plus 1, times shell height, which is 2 minus x, but we're going to have to replace that x with the function value in a second. When your height is right along here, it's drawn in purple, and the largest radius is going to be over here at the tip of it. So what is the y value at this bottom piece right here? Well, that's going to be y equals to 1, and the largest one is going to be when y equals to 4, because the point of intersection right here is the point 2, 4. So let's rewrite this a little bit so that we have everything in terms of y. This is going to go from 1 to 4, 2 pi times y plus 1 times 2 minus, and our function is going to be square root of y and then dy. And for those of you that are interested to work this out, this is actually 118 pi over 15 units cubed.